Mesdames et messieurs, bonjour. Ladies and gentlemen, good morning. Bienvenue dans cette deuxième journée des tables rondes de l'Arbois. Et le thème d'aujourd'hui est un thème qui est particulièrement cher à mon cœur, l'intelligence artificielle. Donc, welcome to the second day. And the theme for today is a theme that's very dear to my heart, artificial intelligence. This artificial intelligence is not something that's it's something that's revolutionizing everything, and it's a transversal technology that has the potential of changing everything we do today. And yes, so many things have been said about AI that I don't think I have to say anything more. So the next speaker, the first speaker we have of today is a French computer scientist specializing in large-scale distributed systems, peer-to-peer networks, and system support for machine learning. She earned her PhD from the University of Rennes, Rennes 1, in 1996, and was a researcher at INRIA from 2004 to 2015. In 2015, she founded Mediego, a startup for real-time content personalization, serving as CEO until 2019. Since 2020, she has been a full professor at the EPFL, leading the Scalable Computing Systems Laboratory. Her work has earned her the Michel Montpetit Prize in 2011, Academia Europea membership in 2013, ACM Fellowship in 2017, and the title of Chevalier de la Légion d'honneur in 2019. Please welcome Anne-Marie Kermerek.
Thank you very much for the introduction. Good morning, everybody. I'm very happy to be here. So I think I'm gonna give my talk in English because otherwise I will use English words anyway. So I'm here to talk about decentralized learning. Let me just check how this is. Yes. So before going into this, I would like to remind you a little bit of history in a sense. So if we go back to the 60s, those two people, actually Vinton Cerf and Bob Kahn, they basically had a dream, and the dream was to connect machines from very different places in order to share documents first, but also make sure that if there were an issue in somewhere on a machine, basically there would be enough replication so that we could recover. And those guys basically invented the internet, and that's a long time ago now, and they standardized a protocol called TCP/IP, and this is why they are very well known. Now, if you think about this, internet is a very decentralized systems. So there is not a single cable between any machine and any other machine, right? It's something that relies on a sort of a local knowledge at each step of the routing process. So basically, this is already a collaborative decentralized system. So we can say this a little bit as the road, right? When I go from Lausanne to Rennes in Brittany, in France, when I am in Lausanne, I don't see any sign saying this is a direction for Rennes. I just see signs saying this is a direction for Paris. And then as I go along, and when I reach Paris, I see sign like, this is a direction for Nantes. And then I know I should go west. And then eventually I see signs for Rennes. So this is basically the routing process. And what it means is that at each step, basically what you do is you rely on the local knowledge to actually move forward. So this is very much what we call a collaborative decentralized system. Now it's very low level, where we're talking cable and routers. Now, later in the 90s, who don't recognize this guy? Okay, you should. Because he did something that was very important, and this is probably what really democratized the internet, actually. This guy, Tim Berners-Lee, had a similar dream. What he wanted to do is making sure that, well, trying to give the means for every scientist in the world to be able to share data over the internet. And as I mentioned earlier, the internet somehow, even though that's a very collaborative distributed system and so on, was not very practical, right? Because this was pretty much a networking protocol. So what he invented is actually the World Wide Web. And this is again a decentralized systems. So what he did was like making sure through two things. One is a common language called HTTP, and the second one is a huge index called DNS. And based on these two things, what he wanted to do is from any machine in the world, you could actually route to any other machine. And not only by knowing the IP address, but by knowing a higher level description, say a newspaper, for instance. Now, what happened though, so all of these were very sort of, collaborative ideas, and in order to serve science and university and so on and so forth. Now, what probably Tim Berners-Lee didn't foresee at the time was that the world will turn completely differently thanks to his invention, and basically that all the data and the business model and everything would eventually rely on a very centralized system. And this is what happened today, especially in terms of all this GAFAM and stuff, where the data now is highly centralized. So not practically, because they're all distributed in many data centers, but I mean, from the standpoint of a company, they belong to a single, the web is now in the hand of a few giants. Okay, why am I telling you this? Because now we move to AI, right? And AI is pretty much what is the next big thing after probably the web. And we are now in a situation where you use AI for pretty much everything. That can be thinking, web search, agent, deep search, and everything. And if you want them to work well, not only algorithms and data are necessary, but systems are actually crucial. Systems is how do you operate these kind of systems. And why is it important? Because we're in these 2 days of breakthrough from science, is because, okay, for some reason I'm stuck here. Okay, it's because AI is also transformative for science, and this is why we need also to have a very efficient system to do this. So why I'm saying is transformative for science is that a very good example of this is actually the 2 Nobel Prizes that we had last year, and whether that was in physics or in chemistry, chemistry, both of them had computer science very much at the core. So in terms of chemistry, this is basically the AlphaFold system, where they manage, thanks to deep learning, to do some research on protein structure and come up with solution that would have taken centuries for manually to do this. And then the second one is a Nobel Prize in Physics for the discovery in machine learning and artificial neural networks. And Jeff Hinton here actually received a while ago the Turing Award, which is the sort of Nobel Prize in computer science. So basically this shows that now AI is pretty much at the heart and the core of multiple science. And this is true for many other things. So now, this is true in biology. So all of this is like kind of discovery thanks to AI. This is true in physics, where it's a very unusual circuit here. This is also true actually in computer science. And now, there were some, thanks to neural networks and AI, there were some discovery in terms of sorting algorithm, which is probably the algorithm that have been studied the most in computer science, but also in design. And more recently, we had the metrics computation, thanks to AlphaEvolve, who were sort of made much better with this. Okay, so if I want to make a pause at this point, what I want to say is that initially the internet and the web were thought as very decentralized system. Now we are the era of AI, and this is crucial for science to have efficient systems. And basically, my own dream, in a way, is to apply this notion of decentralized system into the AI context. Okay. So far, what happens is that whenever you have some, Chat GPT or whatever kind of Gemini, whatever kind of your favorite AI, basically, the thing that happens is that it's already highly distributed, but it's highly distributed in data centers. So basically, the data is centrally collected in data centers, say, the Google data center, the DeepMind data center, name it. And then the AI models are actually parallelized this way, right? So in a sense, the data still need to be collected by a central entity. But now if you think about this, what happens is that, so this is pretty much the figures for the data out there today. So there is a number of data, which is a small amount, which is the higher part of the iceberg, which is indeed used for training those algorithms. And then there is a number of public data that are not always used for training, but could be found. And then there is a huge amount of data, which is not used because it's in silos, basically, say, hospitals data or spatial agency data or this kind of thing that are not public and that are not used for training and could be useful actually for the efficiency of AI. Now, in addition to this, there is also this notion when it comes to processing data, centrally, is the notion of privacy. And basically, even ChatGPT warns us that we need to be careful because it must be used for training. And the matter is that sometimes there are sensitive data. Now, sensitive data can be very different things. So typically, if you take the context of a hospital, the patient data is not something you have the right to share. Even if you think about our own, SMS history, for instance, do you really want to share these things? Do you want to share all your picture and everything? So what's going on with sensitive data? And basically, how do we know that such models of AI are compliant with privacy regulation? The thing is that we don't know. So the solution, if you don't want to share your data, well, just don't share it. And this is what I want to tell you a little bit more about now, is that if you want to still have AI models that work well and that in which they deal with sensitive data, well, in that case, you can still make this in a highly decentralized way, and they will be efficient. And this is what I want to talk about today. Okay, so let me just go directly with this. So I'm taking the example of a hospital here. So now I'm going to tell you how collaborative machine learning works or collaborative AI works. Imagine a network of data. So they are connected according to a given topology. There is no central entity that knows everybody, that has a local knowledge, global knowledge. But yet those different hospitals would like to train or collaborate to make AI systems efficient, right? And they have data that they don't want to share just because they don't have the right to. So now there are two things they can do. They can do some collaborative training. Training is basically how you come up with models that are efficient. And they can also do collaborative inference. Inference means when you have a query, you can collaboratively get the answer from the difference. I'm going to focus on collaborative training here. So the idea is that you want all this set of hospitals to come up with a model which has been trained using the entire set of data without sharing any data, okay? So what a Google/GAFAM would do is that collect all those data, all this data in a data center and then train the model, okay? In this situation, we don't want to share data at all, sorry. So how do we do this? Basically, the data stays where it is generated. And this is very simple. What happens is that each entity is going to train its own model locally based on its own data set. Okay? Does this for a while and then exchange those model parameters with its neighbors according to a given topology. Now, after that, there will be some aggregation at each node, and then they train again their models. So basically what happens is that your own data is distilled in the network through the model parameters that travel from one node to another. Is that clear at this point, or did I lose you? Clear. Okay, good. Right. So, so this is very much what happens, and then we iterate this way, and up to a point that every node will have the same global model, which will have been trained using the entire data sets, but without sharing any data. Right now, you don't share data, but what do you share? You share the model parameters, and that can also potentially be an issue. So let me just go back to the two types of systems that we were talking about: data centers, centralized, and then decentralized systems, which are also called peer-to-peer systems. And I would just want to point out the different challenges that we have. So the first one is that the data might be very heterogeneous. So if you collect data centrally and you have very heterogeneous data, say, take the very simple example of a classification algorithms, where you want to distinguish cats and dogs, right? If you have, or whatever, if you have data collected centrally, then what happened is that they will be all collected and then we distribute it for the computation, but in a homogeneous way, right? Now, imagine that I'm a machine with only cat's pictures and Claudie has only dog pictures. Then it's very heterogeneous. So each time we will train locally our model, right? My model will be really trained for cats and her model will be retrained for dogs. And then we aggregate. So we will get there, but it will take some time. So that's one of the challenges. The other challenge is the system heterogeneity. When you're in data center, you have machines which are pretty much all the same. They have a high bandwidth, a lot of memory, and so on and so forth. When you are in decentralized system, you might have very different characteristic with respect to computation, network capabilities, and everything. And finally, and this is what I want to talk about today, is about the privacy. So again, in a data center, there is no privacy at all, right? The data is collected locally and used, and that's it. Now, as I told you, in a decentralized system, there is some privacy already because you do not share the data. Yet, you have a number of information that goes through the model parameters that you exchange. So even though you don't share the data, you still have to add additional mechanism to make sure that your system is private. And this is what I'm going to illustrate now. So again, there is a number of challenges, and I'm going to focus on privacy today. So the first potential attack that you can have in decentralized learning is what we called membership inference attack. So again, the model parameters are the only information that you share between nodes at the training time, okay? Now, out of these models, what you can run is basically an attacker can actually use these parameters and try to find out whether a specific data item sample has been used for the training. So typically, my medical record, has this model been used using this? So needless to say, this is some attacks which are quite expensive, but still that can happen. And, this is something that we basically need to take care of. The other thing, which is another even more powerful attack, is this is called gradient inversion. So the idea is to reconstruct the entire data set of a given user from the model parameters. So basically, in this attack, what you show is that based on an attack on these model parameters, you can reconstruct. An attacker can say, well, this has been trained with the entire data set of Anne-Marie Carmack. And the last one is called the linkability attack, and that is something that basically matches a user and a model parameter. So it's not only that this has been trained with a given data set, but with a given data set and the username. So all those attacks are something that we want to fight against. Now, I'm just giving you an idea, and I'm very happy to have, for once, images in one of my talk. So here is the original data pictures that you have. so that the model has been trained with, okay? Now, this is a specific attack that has been run on a decentralized learning algorithms where parameters were shared. And what we can see with this is that you can recover pretty much exactly the right sample with this kind of attack. So it is quite vulnerable. Okay, so what do we want to do? So what we'd like to do is to have some privacy-aware decentralized learning approach, which means that you want, even though you share the model parameters, you still want, you know, your system to be resilient to the attack I just presented. So one way to do it is called sparsification. Sparsification means that you don't need to send, because we all know that AI algorithms are over-parameterized. So what you don't want to do is send the entire model parameters. So you just sample these parameters. And as a matter of fact, if you sample correctly this, you can have good solutions. So for instance, if you sample at random, say that instead of sending my whole set of parameters, I'm just going to send an eighth of the parameters, but picked uniformly at random. In that case, what you can see is that you cannot, this is quite efficient because you cannot recover, you cannot attack the system. Now, if you choose your parameters in a different way, which is basically saying the parameters say that are the most important, you know, according to some metric, then you see that you are more vulnerable. So basically, you can get privacy with this random chunking, sparsification thing, but then it's very hard to get both accuracy and privacy. So because if you sample like this, you will have a much lower accuracy. Which is illustrated here. So this is the accuracy. Ignore the blue curve. So the red one shows the right accuracy, and the green one is the one that works well with respect to the attack, but doesn't work well with respect to accuracy. Now, another thing that you can do is that you can add some noise. This is called differential privacy. So basically, it means that instead of sending your raw model parameters, you just add noise to this, and then do the aggregation this way. Again, and I'm not going to go into all this plot here now, but again, what you can get is you can actually have a high level of privacy, but at the price of a loss of accuracy. So the more noise you add, the better you add privacy-wise, but the more noise you add, obviously, the less accurate you can be. And the last thing is actually everything related to secure computation. So for example, homomorphic encryption, I don't know if you know this, it just means that you can actually do some operation on encrypted data. And that's very secure with respect to privacy. This is very good with respect to accuracy, but that requires a lot of coordination and it's very costly. So anyway, the question that I'm just going to take 2 minutes to show you is that can we have it all? And yes, the answer is yes. And just to give you a little bit of a technical details of one approach. So basically, this approach, so this is something I've been doing with some colleagues in France at INRIA and also my students. So in a nutshell, what we do is that, again, these solutions just rely on a chunking mechanism. So as a node, as a hospital, I'm not going to be one single node anymore, but I'm going to be like X virtual nodes. And what that does is that when I have my model here, when I need to send it to some neighbors in my topology, network topology, when I need to send it to some other nodes, I'm not going to send the entire model, but I'm just going to chunk it in small parts and send just one bit. And eventually, this will continue going this way and provide some guarantee with respect to privacy without hampering accuracy. So this relies on three different things. The first thing is a chunking. I never send all my model to everybody. I'm just sending part of my model. So now as a node where I would have needed to send my model, say, to Rachid, now instead I'm going to be divided in a number of nodes, and each of them will send, one to Claudie, one to Michel, one to Rachid, and so on and so forth. So this is now the communication topology is not among real node, but virtual node. So that's the second thing. And the last thing is that as opposed to what I presented before, we still have the full sharing. we chunk our model, send it over, but we still have the full sharing. And the last twist is that we have randomized topology, but that basically too much of detail. Let me just show some results before concluding. So this is the original images that you have. This is what the traditional distributed decentralized learning algorithm would do, which means you can recover images in a very precise way. So this is very vulnerable to attacks. And now this is our system with increasing number of virtual nodes. So here I chunk my model in 2, here in 4, here in 8, here in 16. And what you can see is that this is much more difficult to attack as before. Okay, so just wanted to give you a little bit of what the kind of research that we can do in this area. And I would like to basically finish with this. So we have seen several eras of web 1.0, 2.0, 3.0 was the blockchain-based kind of things. Now we are the era of web 4.0, which basically means that we can come up with fully decentralized, distributed-based, agent-based AI. And this is what I'm very interested in. And I think it's the right time now to do these kind of things. So there's still a lot of challenges to have in this area. So obviously something that but I think you guys yesterday had an energy kind of day. So obviously, you know, if there is something that we need to take care of at some point is the sustainability of such approaches. So I was mentioning privacy awareness today. But there's also fairness, you know, personalization of these systems. And one thing which is very important is robustness. And I think you will have later today at noon, if I'm correct, a talk about robust AI. So this is pretty much what I wanted to say. I wanted to give you a little bit of an idea of the challenges that you have behind decentralized AI. And I'm pretty sure that we are there now. Peer-to-peer system have been around for a while, but I have the feeling that this is a very good time to actually unlock its power. Thank you very much.
Thank you. So we have time for a few questions. Yes.
Bon, on peut parler français quand même.
On peut.
Oui, bon, d'abord c'est extrêmement intéressant, mais ce qui m'a un peu surpris, c'est que vous ne parlez pas de federated learning. Quel est le lien entre collaborative decentralized learning and federated learning?
Alors, c'est le slide que j'ai passé un petit peu rapidement au début parce que donc effectivement, les deux font partie du collaborative learning. Seulement, donc dans l'apprentissage fédéré, ce qui se passe, c'est qu'on a un serveur. Donc, il y a quand même une notion de centralisation et il faut, mais c'est une autre approche. Mais en tout cas, le fait qu'il y ait un serveur, donc il y a un serveur, chaque client s'entraîne localement, renvoie le modèle à son serveur et c'est le serveur qui agrège le tout. Donc, ce sont des approches qui existent et qui sont déployées. Après, il faut ça ajoute par rapport à au decentralized learning, ça ajoute une sorte de nécessité de faire confiance à ce serveur, en fait.
Oui, bien sûr.
Voilà. Donc, mais sinon, c'est aussi une forme de distribution, mais c'est un système distribué beaucoup plus simple en quelque sorte. Donc, il y a un certain nombre de challenges qu'on avait auparavant qui sont un petit peu réduits parce que justement, il y a ce point de synchronisation.
D'accord. Merci, ça m'intéresse beaucoup. Et puis, j'ai vu que vous parliez de inverse gradient. Il y a des mathématiques derrière ça?
Oui, alors oui, il y a des mathématiques derrière tout, évidemment. Oui, alors il y en a. Oui, alors les mathématiques qu'il y a derrière, en gros, ce sont des algorithmes. Quand on fait on réentraîne, on utilise vraiment la même chose, c'est-à-dire le stochastic gradient descent.
Oui.
C'est exactement la même chose qu'on fait quand on est un attaquant qui doit faire ce genre de choses.
Inverse, alors.
C'est-à-dire qu'on essaie à partir du gradient
oui.
qu'on a,
oui.
on essaie de voir quels sont on fait des tentatives probabilistes. Au début, on initialise de manière aléatoire les échantillons et on essaie de s'approcher le plus possible du gradient, en fait. Voilà.
Merci.
Voilà. Et par contre, il y a là où il y a des mathématiques, je vous en ai pas du tout parlé ici, c'est dans les garanties en termes de privacy qu'on a.
Merci beaucoup.
Voilà.
Merci.
I think it's working. Yeah, thank you very much for this inspiring talk. You have a lot insisted on the, let's say, security, but everything is based on data, as you know. And what about the reliability of this data? And is there any way to check the reliability of the data they are putting in the machine beforehand?
This is a very interesting question. So basically, what your question is, what if the data that I'm using is poison, basically, or bad quality? Yes, that's a very interesting question, orthogonal question, I would say. And yes, we are kind of working on these kind of things. But yes, there are solutions. You can try to correct bias. You can try to detect when there are such things, but it's a little bit what in the category of what I call robust AI in a sense. And you might have some information later at noon today.
Thank you. So one last question.
Well, first of all, thank you for the inspirational presentation. I'll have a complicated question, I guess. It's more technical. But
do you think I can handle it?
We'll see about it, actually. But yeah, thank you very much for the inspirational presentation. First of all, I'd like to ask about datasets. Like, what are the metrics that make us decide what, I mean, a dataset can be used globally or just in, how can I say, in a regional place? This is, first of all, excuse me, I'm not patient. It's very long. Second, we've talked about virtual nodes. How can we control using virtual nodes, especially when we are trying to upgrade or augment, if I might say, the accuracy of our models? Because on a moment when we are using a lot of virtual nodes, we are on a mess and we don't understand the mathematics behind it. So we need to, like, first of all, understand le raisonnement mathématique des choses pour mieux les gérer.
Okay, so two things. So the first one is data set. So basically the data set that we use are sort of data set that are out there for, experiments purposes. Now, all the data, when you talk to hospitals now, this is something they're very interested in because they cannot share, and it wasn't the case 10 years ago, but now hospitals typically do not have the right to share data. Okay, so the data need to stay where it is. And I was actually talking also recently to a space agency, and in that case, it's not that they don't have the right to share data, it's that it cannot because they're way too big. So these are two settings in which you can do this. Now, in terms of the virtual nodes, so two quick answers to this one. The first one that I didn't mention is that the aggregation is done at the real node. So basically, you as a node is split into several virtual nodes, which are used for communication purposes. But when they receive some information, then the aggregation is done at the real node. So that solves this problem. And regarding of the mathematical foundation, we basically prove that if you get chunks of the model like this, you basically still converges toward the right model. So I guess that's the answer. But more details in the paper if you're interested. Okay, thank you very much.
Thank you. Thank you. So our next speaker is a French computer scientist specializing in human-computer interactions. He earned his PhD from Université Paris-Sud in 1985 and has been a professor at Université Paris-Saclay since 1992. His research focuses on interaction techniques, collaborative computing, and interactive system engineering. He is a member of the French Academy of Sciences, a senior fellow of the Institut and a recipient of the CNRS Silver Medal. And he's also an ACM Fellow since 2022. He has held leadership roles as director of LRI from 2002 to 2009, and he's a deputy director of LESN. Please welcome Michel Beaudouin-Lafon.
Good morning, everyone. First, thank you to the organizers for inviting me here. It's a very interesting and stimulating event. As was said, I'm not a researcher in AI. I'm a researcher in human-computer interaction. Our group is called XCTU, for Extreme Situated Interaction. And what we do is we work with users. We start with real issues that users have, and we call them extreme users because they push the limits of technology. And these two groups of users are first creative professionals. We've worked with composers, musicians, choreographers, dancers, graphic artists, designers. And the second group of people we work with are people who work in safety critical systems. And we've worked with air traffic controllers, we've worked with currently people operating the French energy grid at RTE, airplane pilots, and also medical doctors. Now, scientists are in the first group because they are creative people. You have to be creative to do science. So before we talked about humans, I want to talk a bit about the history of technology. So, as you probably all know, humans have tried to mechanize calculation for a long time. We could start with the abacus, can go even further back. Mechanical devices like Blaise Pascal, Pascaline, the analytical engine from Charles Babbage, and of course the modern computer that we all have in our pockets. Now, the other aspect, and something that everybody has heard about, is Alan Turing and the Turing machine. And the Turing machine is an exceptionally simple machine. You can describe in 3 lines, really, how it works. And yet it's extremely powerful because it can compute everything that is a calculable function, whatever that means in mathematical terms. And every computable function can be calculated by a Turing machine. So it's a very powerful thing. You can create physical ones. But it also has limitations when you think of how it interacts with its surroundings. In fact, it does not. There is no way to do input and output. The program has to be put in there. We don't know how. Someone presumably has to read the output, because if you calculate something and nobody reads it, what was the point? There's no way to interact with the computation as it goes. So the only thing you can do is start the machine and wait. And sometimes you have to wait forever. And there's not even a notion of time. You cannot use a Turing machine to cook an egg. So if you look at the history of computers, in fact, computers were built on this system, a Turing machine of computation. We want to calculate things, usually for the military, like with many technologies that start with military applications. And if you look at the humans in those early computers, well, they were called operators. There were women because it was a low-paid job. Only when it became more prestigious to do this, the men came in and kicked out the women. And there was no notion of what humans are there for in terms of interacting with those computers, except checking that they work. You know that the word bug comes from a physical bug being somewhere in the system that screwed up the calculation. Now, the thing is, it's still very early on. Some people realized that you could use computers to do different things that are not mere calculations. And one of the most famous one, maybe the most famous one in the early times, is even Sutherland, who created Sketchpad, a graphical system where you could interactively with a light pen create diagrams, create CAD models, have the system solve geometric constraints in real time, like making things orthogonal or parallel, an object-oriented system before the word even existed. All the things that Sketchpad and even Sutherland invented, we use still nowadays in systems like Illustrator or your favorite drawing program. He also is a guy who invented virtual reality, by the way. Then, mostly at the same time, Doug Engelbart wrote a very influential paper called Augmenting Human Intellect, and created the system NLS Augment, where his vision was that the problems of the world were too hard and complicated to be solved by a single individual or a single machine. And so you need to put together the power of human intellect with the power of machines. And this system was a collaborative system. it combined hypertext, real-time document sharing, and video conferencing. And he gave a demo in 1968, which is known as the mother of all demos. An amazing thing. I encourage you to go check it online. So 60 years ago, we had the web, Google Doc, and Zoom working together. And then a few years later, in the 70s, with people who have worked with Engelbart in particular, Xerox, this Palo Alto Research Center, created a series of computers and invented the personal computing workstation and the graphical user interface, so GUI. And in 1981, they commercialized the first graphical workstation. And it looked like this. And if you look at it, it has menus, it has documents, it has cut and paste. It has everything we still use nowadays. Now, the star was a commercial disaster. It was way too expensive. They didn't anticipate there could be a business for creating software for these machines. It was closed. But it paved the way to the Macintosh. And the Macintosh was, as Apple likes to put it, initiated the personal computing revolution. And people who bought a Macintosh didn't buy a Macintosh to calculate stuff. There was no spreadsheet even in the first Macintosh. They used the Macintosh to create fancy documents, to do paintings and drawings. With HyperCard, they actually could create their own environments for teaching and learning. And so the vision that was underlying this line of work, I think, was nicely put together by Steve Jobs, who said many times, a computer is like a bicycle for the mind. Now, this can look like sort of a cute image, you know, an evocative image, but in fact, it was based on an article he had read years before, published in Scientific American, where someone had plotted the body mass of a number of animals and in fact also human-made things like helicopters and jet fighters, and vertically also on a logarithmic scale the cost of transportation, how much energy you need to move that object or being around. And if you what they called man at the time, we would say human these days, was sort of in the middle here, so not very good. But if you put the human on a bicycle, it's more energy efficient than anything else on Earth. And the bicycle for the mind is that. It's the idea that if you combine the power of humans with the power of technology, you can do much, much better than the sum of the parts. Now, this notion that interaction, in fact, gives more power is something that was somewhat theorized by Peter Wegner, a researcher in formal systems. And in a paper in 1993, which to me was a very a revelation in a sense, paper called Why Interaction is More Powerful Than Algorithms. I was working in a lab at the time where everybody was doing math for computer. And I was there doing my little graphic stuff on the graphic machine, and that was the guy they came with to when someone was visiting and they needed a demo because I was painting pretty pixels on screens. And here I have this guy, very respected in the community, saying, well, interaction is more powerful than algorithms. Well, the paper created some controversy. I'm not going to go into this. But his point is that an interactive machine, something that interacts with the environment, can harness the power of this environment, can find resources in the environment for doing things that it cannot do by itself. And this is exactly what interests me in interactive systems where you combine humans and computers. Now, parallel to all this, another thing that was happening is that another perspective on how to combine human and computers, and that was the project of artificial intelligence. In 1956, the famous Dartmouth Summer Research Project put together a number of prominent researchers to discuss the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. This is the old Cartesian idea that, you know, our brains is a little, well, in Descartes' time, maybe a mechanical thing, more modernly, an electronic computer, and therefore, yeah, we can simulate it. in fact, this idea of machines imitating humans comes back to Turing again, who is also very much well known for the imitation game, as he called it, or what is known now as the Turing test. And the Turing test is about how can you create a machine that will fool a human in thinking it is a human. So a human is presented with two transcripts of two conversations of a human, one with a computer and one with another human, and you have to decide which is which. And if you cannot tell, then the computer wins the game. Now, AI has been sort of driven by this idea of imitating humans ever since then, and there's been a long list of approaches that also use words like learning, like logical reasoning, like knowledge representation, that are very much features of human intelligence. And one of the key aspects in there, I think, is that there's a shift from things that were purely algorithmic in the classical term, deterministic, rule-based, towards more statistical, probabilistic approaches. I'll get back to this. And of course, at the bottom here, you have the well-known GPTs and LLMs, which is the latest in this long line of evolution, and maybe there will be more coming. One of the problems with this system is that, and I think because they are probabilistic in nature and statistical, they have a few issues. One that is well known is they hallucinate. I don't like the word hallucinate. The system does not hallucinate. The system adds zeros and ones, like it's the only thing it knows to do. We perceive it as hallucination when it spurred out something that we don't believe in or we know is false. The first time I used ChatGPT, it very confidently told me that the main article in my area was by someone I'd never heard of. The whole article had been invented by ChatGPT. When Meta put out an LLM fed with all the scientific articles, within days, people had it write articles that convince you that eating shattered glass is good for your health. Very convincingly, with references to real articles this time, saying, well, silicates are good for nutrition. Silicates, crushed glass, same thing. So hallucinations, serious problem. The other thing is, everything has been driven by interacting in natural language. Maybe because it was influenced by the imitation game, which was based on the transcript of natural language. But natural language is not always the most efficient way of interacting and of delegating a task. You know, how would you teach someone to ride a bicycle? By reading a book? I don't think so. There are many things we do, many things we know, many things we learn that we don't even know how to express in words. So yes, natural language is important, but it's not the only way. And finally, there is this thing that if you put a human in front of a machine, whether it's a mechanical machine, an electronic one, or whatnot, there is this cognitive bias called automation bias. And that's the over-reliance on automated system to trust machines more than trust humans. And so it means that imagine a doctor who is to give a diagnostic to the patient, and the AI system is telling the doctor, well, this is the diagnostic. If the doctor doesn't really agree, is it going to take the risk of contradicting the machine? Well, much less so than if it's a colleague trying to tell him the same thing. And so this notion that we're trying to make systems that are better than humans, you read every day in the news, AI is now better than humans at doing this and that and the other thing. Well, what does better mean? Usually it means better on average. Better on average. Better 90% of the time, 95% of the time. But 5% is still a lot. Even 1% is a lot, especially if when you get it wrong, when the system gets it wrong, it can have dire consequences. Would you trust an AI system without human intervention to give you a medical diagnostic, to give you a medical procedure, to give you a medical ordonnance? Would you trust it to be your lawyer, to be the judge, Would you trust it to fly the plane that you took to come over here? Would you trust it to teach your kids? These are all reading every day. Yes, this is going to be the tomorrow. Are we really wanting to do this with systems that are so susceptible to hallucinations? And when we say the machine is better than the human at this or that, the other thing, it's a lie. Because you're not just against, in a sense, the machine. The machine has been programmed by humans, fed by data coming from human. If you take the example here of the first big victory of computing over human intelligence with Deep Blue, the IBM computer beating Kasparov in 1997. Not only the system had been programmed by chess experts and programmers, but they reprogrammed it in between the games after watching the game themselves to figure out, how to make the system better. And that's what's happening today. The ChatGPT you used yesterday is not the same you're using today, is not the same you use tomorrow, because it's constantly being reprogrammed through reinforcement learning. So this idea that it's human against machine and the machine is to get better, I think is a fallacy. And not only is it a fallacy, but it also degrades the role of humans in those systems. In AI systems, humans are seen as a source of data for the algorithm. Usually they're not retributed for providing this data. They're also a source of problems. Humans make errors. And so the system is to fight those errors. More and more humans are components of the machine, where when the machine cannot do it or cannot do it yet, you ask humans to do it instead. So that's all the reinforcement learning done by humans, because we don't know how to make better systems without having humans in the loop. And speaking of human in the loop, that's an expression you hear a lot, saying, oh, we put the human in the loop. Aren't we great? Well, usually you put humans in the loop to make the system perform better, to improve the algorithm. Now, in our research group, we like instead to talk about computer in the loop, where the measure of success is not whether the algorithm is better, but instead whether the users perform better with the help of the algorithm. That's a shift of perspective. The underlying AI can be the exact same system in both cases. It's just a different angle. But it's a different angle that I think has consequences on what we see as a future. And when you want to look to the future, don't look to scientists, go to Hollywood. In Wall-E, the future is seen as, well, we'll have systems that do everything for us, so we can sit down, drink carbonated water, and watch videos all day long. Isn't that great? I prefer the future in Minority Report or Iron Man. Well, I would prefer to also have women there in pictures, but where technology is enhancing human capabilities. And AI can enhance user capabilities. And so to do that, I think we need to play not on trying to make systems better or similar or imitate humans, but play on their differences between the machine and the human. And Paul Fitts, already in 1951, 75 years ago, came up with this list called the Haba-Maba list. Pretty well known. Humans are better at versus machines are better at. And he says, humans surpass machines in the detection, perception, judgment, induction, improvisation, long-term memory, while machines surpass humans in speed, power, computation, replication, simultaneous operations, short-term memory. This was done 75 years ago. I think it's pretty much 100% true. So we know what are the strengths of each side. And so the goal is, once we know that, can we combine them in ways that then lead to even more powerful human AI combinations? This study was published recently, December 24. It's a meta-analysis of about 100 papers that have compared humans alone, AI systems alone, and human plus AI systems for similar tasks. Very different types of tasks, but each study was for a particular task. What they found is that in 58% of the cases, the part in red here, the human plus AI group performed less well than the better of human or AI. Only in 42%, the human plus AI did better. And in fact, their results are a bit more subtle, and I encourage you reading the paper. What they found is that in general, in tasks that involve decision-making, using an AI generated performance loss. But in tasks that involve creativity, using an AI generated performance gains. So it means there are areas where maybe AI is more useful than in others. They also observe that when humans are better than AI alone, humans alone better than AI alone, using an AI usually increases performance. But if humans are less good than AI to start with, then combining humans and AI leads to performance loss. Which means that you have humans that are already expert if you want the AI to bring an advantage. Which is an issue because AI systems, because of automation bias, tend to lead to de-skilling. People trusting the AI and sort of sitting back and letting it do its thing. So this raises a question of who should benefit. And let's turn to evolutionary biology for a minute. In evolutionary biology, researchers have studied the relationships between species and the long-term effect of those relationships on species. And there's a lot of fancy terms here. You probably have heard of symbiosis and parasites. These different arrows show types of relationship where one species benefit, is neutral, or is harmed, and same thing for the other. My eminent colleague, Wendy Mackay, who also happens to be my wife, and a psychologist by training, has come up with this analysis of saying, well, instead of two species, let's put humans on one side and intelligent systems on the other. And let's look at what's happening. So can this help us anticipate whether intelligent systems will replace users? Is replacing users, humans, good or bad? Well, it depends. If it makes you lose your job and your income, it's pretty bad, I would say. Will it lower their skills? I think it's pretty bad too. Or will they enhance your skills? So if you look at two of these relationships called commensalism and parasitism, so both cases are beneficial to the intelligent system and either neutral or harming on the human side. Well, there are many situations where AI is in fact creating those relationships. I talked briefly about reinforcement learning by human feedback, where OpenAI, for example, employed armies of workers in Kenya for very low pay, doing very boring and mentally actually harming tasks to make ChatGPT less toxic. AI companies gather user data without informed consent, your personal data, the creation of artists without compensating them. I think this is at best neutral on the human side, not particularly beneficial when you think of all the artists, the writers, the authors who are fearing that their jobs are going to be replaced by AI tomorrow. I talked about hallucinations, which can lead to bad decision, and when I mean bad decision, it can kill people. And also, the system, again, through other cognitive biases, lead to behavioral control of humans, people becoming addicted to things like TikTok and others, which are driven by algorithms that always feed you the next thing that makes you want to look at it. And addiction can lead to things like people committing suicide. And of course, we briefly mentioned before environmental cost, which is a whole issue in itself. So the thing is, can we instead look at mutualism, which is a symbiotic relationship where both benefit? Now, symbiosis is something that was envisioned very early on by Licklider, for example, in a paper called Human-Computer Symbiosis. Doug Engelbart's notion of augmenting human intellect was also very much this idea. So I don't have the recipe to do mutualist system, but have a few examples. So we created 3 systems in our group that were based on this idea of how can you have intelligent systems behave in a way that is beneficial to the humans. So the first one was, I mentioned we work with artists, here with designers who create mood boards, which is a key activity for a designer, where you gather images and a source of inspiration when you are to do the next, I don't know, fashion collection or the next design of something. And it's a very intense job. And so we created this system where the user can control the agentivity, the agency, where the user can control the agency of the system. The system is always working in the background, looking at what you have on your board, analyzing the images, the colors, the semantic meaning of those images, even their sizes, so you can make them bigger if you want to give them more importance. And the system is suggesting things at the bottom, and you're free to look at it or not. The system can also so respond to search queries, can create tag clouds that are a source of inspiration. And what we found is users really like this notion that, you know, they didn't have to write prompts, and the system could sit in the back or be more proactive. Recently, we published this paper at the main conference in our field called Fusain. Fusain in French, you know, it's this drawing tool, but it also has AI in it. And so we created this intelligent pens that can pick patterns from a source image and apply it to a destination image by just painting over it, and then you turn that into a prompt to a Gen AI, and the system would generate a new image based on that. And again, people really liked this sort of back and forth and an iterative process. And the last example, very quickly, is something we did a bit longer ago called Big Bayesian Information Gain, where we did something counterintuitive. Instead of helping the user by giving the user the most likely answers we think the user is seeking based on, you know, probabilistic data that we have accumulated, we challenge the user. We challenge the user by giving the set of possibilities so that the user answer to it will give the system the more information in an information theoretic sense. Hence the term information gain. And this led to performance improvement of 40%. Now, 40% in our field is really huge, because it's 40%, it's not the computer going 40% faster, that's easy. It's the human being able to achieve a task 40% faster. It's as if I could tell you, well, here's a pair of shoes that will make you run 40% faster. We don't know how to do that. So we did that with that example. Now to the concluding remarks, which I think are going to take a little bit more than 2 minutes. First of all, what I call the myth of perfection. A lot of us here, including me, are engineers. Engineers like to think they can make perfect systems. And we always think, well, yeah, it's not perfect, but the next version will be, and it will get better and better. But then at the same time, with AI, we're trying to make systems that imitate humans. And I think humans are not perfect, and it's not human to be perfect. We don't like perfect humans. In fact, we strive on mistakes and errors and accidents. And in science alone, many great discoveries were done by accident. An example that comes to mind is penicillin and penicillin. Fleming, thank you. So I think there's a contradiction in terms here in making perfect AI systems that behave like humans. Second thing is this shift from deterministic to statistical system leads to brittle systems. We've seen it with hallucinations. There's a recent paper in Communications of the ACM that shows that when you try to align the AI system with human values through reinforcement learning, that leads to separating the states that are good versus the ones that are bad. But that also makes it easier to attack the system, to shift it towards the dark side, if you wish, and making it do things that you really don't want it to do. So again, there's kind of a paradox or an inconsistency here that we need to think about. In fact, when I speak to my AI colleagues, they tell me, well, we know how this system works. We don't know why they work so well. So can we really trust the technology when we don't know really why it works so well? That's a good question. So of course, I'm not saying we should not use AI. Of course we should use AI. The question is, how can we use it? And I think that currently we have too much separation between my field, human-computer interaction, with things of computers as tools, our AI that thinks of computers as servant who can delegate tasks, and the whole area I didn't talk about, mediated communication, where we use computers to mediate social interactions. I think these fields have to work together. And instead of treating people as a source of data, a target for behavioral control, or a guardrail against errors, we should build on human skills and strive to empower humans with mutualist relationships. Thank you.
Thank you. So we have time for a few questions before 10-minute break.
Je vais te remettre en français.
Oui, oui, tout à fait.
Le mutualisme, en fait, a été découvert au 19e par le lichen, par la biologie, au moment où deux espèces différentes vivaient ensemble. Et il a été appliqué par la suite à l'interaction de l'homme avec le microbiote. Et on s'aperçoit aujourd'hui, si on regarde la biologie, que le microbiote n'arrive pas au hasard. Il existe un système immunitaire qu'on pensait fait en réalité pour rejeter les bactéries, mais qui au contraire attracte les bactéries et essaye de faciliter la relation entre entre le microbiote et les cellules humaines, à vrai dire, pour former un homme. Donc ma question est la suivante. Est-ce que, par similitude avec la biologie, il ne serait pas intéressant en fait d'inventer un système qui facilite cette interaction entre l'homme et le computer?
Oui, absolument. Et j'ai envie de dire, c'est ce qu'on essaie de faire. C'est-à-dire que les systèmes d'IA sont extrêmement performants et on ne dit pas qu'il faut en faire forcément des différents. En fait, on peut utiliser même très souvent des systèmes beaucoup plus simples, je dirais, beaucoup moins coûteux en énergie, etc. Et si on les combine proprement, correctement, intelligemment avec les capacités humaines, alors on crée cette interface. Et notre domaine, c'est l'interaction homme-machine. Notre sujet d'étude, c'est l'interaction en tant que phénomène, et c'est comment on peut rendre des qualités de ce phénomène plus positives. Et je pense que l'inspiration de la biologie est une bonne source, en particulier parce que souvent on cite Darwin en disant survival of the fittest, etc. Mais en fait, bon, Darwin était aux Galapagos où la vie n'est pas très dure pour les animaux aux Galapagos. Et ce que je sais de ce que ma femme m'a expliqué, c'est qu'il y a un autre chercheur, Kropotkin. Alors oui, mais il y a aussi, voilà, mais il y a un chercheur qui étudie les espèces en Sibérie, où la vie est un petit peu plus dure, et où il a observé de la collaboration, du mutualisme là-bas, et qui allait à l'encontre du dogme de Darwin. Donc oui, je pense qu'il faut aller vers là, et je suis convaincu que la biologie est une source d'inspiration. Mais pour ça, il faut s'intéresser au phénomène de l'interaction lui-même et pas juste à l'aspect purement technique, qui est certes important. Et c'est pour ça que c'est un domaine pluridisciplinaire où on combine l'expertise en sciences humaines et sociales, en psychologie, en sociologie, avec l'expertise technique.
One last question.
Thank you so much for the presentation. My question is a little bit related to, as you said, human-machine and machine and the human relationship. But there is this new problem that is rising when it comes to humans' relationship with machine. And it's mostly related to starting relationships with AI. I think there was a research in 2022 that 300,000 people started developing relationships with AI. My question is, so we have human-machine and machine-human, which one is doing better? But in a situation where we have relationships developing, are we still talking about which one is doing better? Or is it a different equation in that situation?
You're absolutely right. I think we are in a different type of relationship where it's not about performance. And I think the way the algorithms are programmed to create a form of addiction has effects on mental health. People who develop this relationship with those machines project human qualities on the machine. Usually they do it because they don't find humans who can sort of help them or respond favorably, so they prefer to engage with the machine. So yeah, it's not which is better. The question is that a good thing to do? And I think fundamentally, technology is never good or bad, but neither it is neutral. And this question is how to use it. And so I cannot say and I cannot judge, is it good or bad to have a relationship with the machine? But we need to educate people about these effects. We need to educate people on how to use ChatGPT, how to use the web, how to use technology in general, and in particular to warn them against the possibilities of addiction and other issues. I also think companies have a large responsibility in this. There was a person who left Meta when she discovered that Meta knew absolutely that the algorithms used in their products were affecting the mental health, especially of young women, and they continued doing it because it provided more income. The companies are not going to change by themselves. So we also need policymakers to intervene. And I happen to be the chair currently of the ACM Technology Policy Committee for Europe, where we respond to every consultation by the European Union on the implementation of the AI Act. We inform politicians about those risks. They are the ones who have to take action, because I don't think, and I think this is echoes what was mentioned yesterday by Dominique Strauss-Kahn, is we're facing really a paradigm shift. And so we need actions that comes from policymakers, also from educators, and tell companies to, not do harm.
Thank you. So we have a 10-minute break, so please come back in 10 minutes.